I am Shahin Honarvar from the University of Leicester, UK. I'm going to explain about our framework called QSharpCheck, which is a property-based testing tool of quantum programs in QSharp. This is a joint work with Professor Mohammad Reza Mousavi from the University of Leicester, UK, and Professor Rajagopal Nagarajan from Middlesex University, UK. In our framework, we have implemented the property-based testing technique to test quantum programs. This is the first framework that uses property-based testing approach to test quantum systems effectively. Although it is developed for QSharp programs, but it is extendable to other quantum programming languages as well. The tool package is available at this address. Property-based testing is a type of model-based testing where the tester doesn't write test cases, but the test cases are generated by the corresponding framework from general properties of the system under test. Since it has been a successful testing technique, it has been used in various domains, such as automotive software, telecommunication software, business information systems, and so forth. The process of property-based testing is that initially the framework starts generating appropriate input values. Then each property is run against all of those generated inputs. Then if the property is always valid, the test passes. But even if just in one case the property is not valid, the test fails. Therefore, it is necessary to note that the property has to be always valid for the test to pass. QSharpCheck is developed for QSharp programs. QSharp, introduced by Microsoft, is a domain-specific programming language for expressing quantum algorithms. It is a part of QDK, which is Quantum Development Kit. As a programming language, QSharp uses common elements of Python, C#, and F#. It follows a fundamental procedural model for writing programs with loops, if statements, and common data types. Also, QSharp introduces new quantum-specific data structures and operations. To evaluate the effectiveness of our tool and technique, we took two typical quantum programs, which were teleportation and superdense coding programs. Then we defined a number of mutation operators to inject potential faults in the program on the test, and studied which mutants could be killed by the test cases generated by our technique. The calculated mutation scores were 80% for the teleportation program and 60% the superdense coding program. These scores show that our approach is promising. In the rest of this video, I'm going to talk about the testing language and the structure of QSharpCheck, and also the way we measured its effectiveness in more details. To test the quantum program by QSharpCheck, firstly, a test script must be provided. The language of this file must be complied with the QSharpCheck language and syntax. In the preamble part of this script, first a test name is given. It can be any arbitrary name. In the next line, the values of test arguments are determined. In the next slide, it will be explained fully that what is meant by these four parameters. In the next phase, a number of qubits or qubit arrays are allocated. Also, if needed, the tester can determine the state of the allocated qubits to a particular state or a region in the Bloch sphere by choosing specific theta and phi value intervals. The angles theta and phi are the angles in the Bloch sphere associated with the amplitudes of the qubit state. If any other data types are required in the precondition part of the test, they can be written here as well. In the next part, the exact signature of the QSharp program operation on the test is provided. Ultimately, based on the program on the test, any combination of the built-in assertion methods is used. We have provided several assertion methods in QSharpCheck. Assert probability is used to test the probability of observing a qubit in a given state. It takes three arguments: a qubit, a state, and the expected probability of observing the first argument, which is the qubit, in the second argument, which is a state of the measurement. Another assertion method is assert entangled, which takes two qubits as its arguments to test whether or not they are entangled. Set equal takes two qubits as its arguments to compare their status and to check if they are identical or not. Assert teleported is created specifically to test quantum teleportation, as it is a significant protocol in the quantum realm. Sometimes the output of the quantum program may be the result of applying a transformation on the input arguments. To validate this, we have introduced a assert transformed method in QSharpCheck. As it was mentioned, the second line of test script refers to the test parameters. The first parameter is the number of concrete test cases to be generated from the property. The second one is the statistical confidence level for the property to hold in test analysis. The third one is the number of qubit measurements, and the fourth parameter refers to the number of experiments over which those qubit measurements are replicated. The last two parameters are there to obtain the data for statistical tests. It is optional to provide the value of these four arguments by the user. If they are not provided, QSharpCheck will use default values, which are 10 for test cases, 99 for confidence level, 350 for the number of measurements, and 300 for the number of experiments. This means that 10 individual test cases will be generated with a confidence level of 99%, and in each test case, the qubits will be measured for 350 times, and these 350 measurements will be replicated over 300 times. The larger the values of the last two arguments, the more reliable the test results will be. But since the cost of testing will increase, it is required to consider a reasonable trade-off between accuracy and cost. Therefore, the tester can monitor the cost and accuracy of the test by modifying any of the test parameters. In this slide, our framework architecture is displayed step by step. Firstly, the test script is passed by QSharpCheck, and the appropriate test cases are generated by the generator part of the framework. Then the concrete test cases are passed to the test execution engine of the framework. This engine invokes the program under test. Subsequently, the test data will be fed into the statistical analysis engine. As soon as the analysis process is complete, the final test verdict is displayed to the user. In the statistical analysis engine of QSharpCheck, we have used different statistical concepts and methods such as binomial distribution, chi-square test for independence, independent samples t-test, and hypothesis testing. Chi-square test for independence is specifically used to check the entanglement of two qubits. T-test is particularly used to test the equality of the status of two qubits. In hypothesis testing, two basic definitions are necessary to be explained: null hypothesis and alternative hypothesis. Null hypothesis claims that no difference between the observed counts and the predicted amounts is made in a set of measurements, while alternative hypothesis is the complement of the null hypothesis. For example, when assert entangled is used in the post condition of the test script, the null hypothesis is that the two qubits are entangled, while the alternative hypothesis is that they are not entangled. Then, based on the outcome of the statistical analysis engine, null hypothesis is rejected or failed to reject. As an example, here we see a test script to test the teleportation program. The first line, teleportation property, is the name of the test property. The second line relates to the test arguments, which were explained previously. The next part includes 3 lines, which are about the initialization and allocation of the required qubits. As you can see, the state intervals for QAlice and QBob are all 0. It means that each qubit is initialized to state 0. However, QMessage's state has been chosen from the specified subspace, which is defined by all values of theta between 10 and 80 in degrees, and all values of phi between 0 and 360 in degrees again. When testing process is finished, depends on the result, the corresponding report is displayed. Here, the green box shows the report of a past test, including the test information such as the number of test cases, value of confidence level, the number of qubit measurements, and the number of experiments. But if the test fails due to an error in the system on the test, a report similar to the one in the red box is produced by QSharpCheck. There are 2 significant points in this report. Firstly, it shows that after how many test cases the test failed. In this case, after 1 test, it failed. Secondly, it tells us what the counterexample is. Here, the counterexample is specified by the values of theta and phi. Therefore, the tester can easily find the state of counterexample qubits in blogosphere. As it was mentioned in one of the earlier slides, we measured the effectiveness of our tool by mutation analysis, and good scores were gained in testing teleportation and superdense coding programs. Now I explain about some basic definitions of mutation analysis and how we evaluated our tool effectiveness. The artificial errors inserted into a program are called mutations. For example, if there is a main code that, if the result of measuring Q0 is equal to 1, then apply Z operator to Q1. Now we insert an error here and we mutate the code by changing Z operator to X operator. The outcome of a mutation operator implementation is called mutant. When the test suite detects the change in the code, we say the mutant is killed, since it has been found. To calculate the mutation score, we divide the number of killed mutants by the total number of mutants, and then multiply by 100. In measuring the effectiveness of our tool, we use these different types of mutation operators in the programs on the test. Here, there is an example with each of them to clarify what each means. Statement deletion, statement duplication, replacement of Boolean relations, replacement of quantum operators, changing the order of quantum operators, replacement of a variable with another compatible one. In each case, we tested the modified program with QSharpCheck to discover how many of the mutants were killed by the test cases generated by QSharpCheck. As it was stated earlier, 80% was the mutation score of testing teleportation program, and 60% was the mutation score of the testing superdense coding program. In this video, our framework called QSharpCheck was introduced. It is the first property-based testing framework which robustly and effectively tests quantum programs in QSharp. Our future research will be about providing data generators that can efficiently satisfy preconditions, extending the test property language to test stateful properties, providing shrinking strategies and effective debugging methods, and also developing an effective mutation tool for quantum programs. Please do contact us if you have any questions or you would like to have any further information about our research. You can download the main paper and the tool package, including the results of case studies, through the provided links here. Thanks for watching.
Shahin, are you finished?
Yes.
Okay. So we enter the question phase.
Okay, sure.
Any questions so far? No, perhaps I can start. Thank you for the interesting talk because it's quite a complete approach. I can see. It's just the one thing. The mutation, that part actually is quite similar to the classical testing, the mutation testing. Have you considered any other like more quantum program specific mutation operators?
Sorry, I didn't hear the last part of your question. So you said it is similar to the classical mutation testing.
Yeah.
Okay.
Yeah, I mean, have you actually considered that there will be more like quantum program specific mutation operators, for example, directed on the superposition of the qubits or?
Well, actually, as it was mentioned in the last slide, we are, extending this research. So we are trying to find some mutational tools specifically for quantum programs. Because as it was mentioned, like, for example, we got 80% with teleportation and 60% with superdense coding. And our question is why in some cases, some mutants were equivalent and they were not killed. So it needs another, phase of research to extend this, measurement of effectiveness.
Okay, thank you. Yeah.
No worries.
Yeah, I see Shahin has a question. Go ahead, Shahin.
Yes, I was wondering that this testing technique property based. So did you implemented your technique in QSharp? Or is it to run on a quantum computer or simulator, or is it on traditional language implementation?
Well, it is actually, it is at the moment, it has been run on simulator because, the QDK has been a simulator on conventional computers at the moment.
Okay, so the implementation of the technique is also in QSharp.
Yes.
And
so it is in Q. So we have developed QSharpCheck for QSharp programs, but the whole idea and concept can be extended to any other programming languages. I mean, quantum programming languages.
Mm-hmm. No, what I was yes, but I was wondering that so can your testing technique can be considered as an application of quantum programs? Your testing tool, for example, or no? Maybe.
Yes. Yes.
So it means that you will check the properties in, for example, in superposition, or how it will work. I mean, it's.
If I have understood your question, are you asking about the properties of the system on the test, or?
No, so you have a system under test which is written in QSharp that you are testing.
Yeah.
And then you have your testing tool, right?
Yes, which is QSharpCheck, the framework. Yes.
So that testing tool, is it a pure? Is it a classical program, or is it a?
So now I understood what you mean. Okay, so it has been written in C#. Okay, so the whole framework is written in C#, and when the tester provides the tester script, so it passes the tester script, and correspondingly it invokes the QSharp program. Because the QSharp program, when you run the QSharp program on a conventional system, you need to have .NET framework as well. So there are two parts. A part is called driver, which is written in C#, and another part is the main quantum program, which is written in QSharp. So the C# part invokes the QSharp part, which is the quantum program. This QSharpCheck framework has been written in C#. So when the tester just needs to provide the test script based on what was explained in the video. So when the QSharpCheck starts the process of testing, it firstly passes the test script, it gains the information, and during the process, it invokes the program on the test, which is written in QSharp.
Okay.
So I hope I have
Yeah.
answered your question.
Yeah,
I think Mohammad is raising a hand. I guess you can start. Mohammad?
Yes, so I think Shahin already said what I was about to say. So QSharp itself is a classical program. QSharpCheck, sorry, is a classical program. There is scope for looking at quantum testing tools that use quantum algorithms for testing. We haven't done that, so we just use classical algorithms for testing. And then even using classical testing, there are still further steps to take.
Yeah, I think that would be really revolutionary, right? So may I ask one quick question again?
Certainly.
So I was wondering that, so it's a very interesting and, one of the pioneering work in testing, I feel that, and so I was wondering that how do you think it will scale? I mean, if we increase the number of qubits, so what do you think, how scalable it would be for like 10 qubit, 20 qubit programs, or what do you think?
Well, you mean like multi-qubit systems? Like,
Yes.
Yeah.
Yes.
Okay. This is another part. So at the moment, we have implemented and created this framework for single qubit systems, but in the future, it can be extended for multi-qubit systems as well. And well, it has its own challenges as well. But yes, it is possible, and it needs another further deep and profound research.
All right. Okay. Thanks a lot.
Thank you.